Hi, I'm Matija Budhrashki, Principal Engineer for Integrated Circuits at RLS, and today I will briefly introduce you the Hall sensors. In semiconductors used to make integrated circuits, two types of charge carrier are possible. In p-type semiconductors, majority carriers, known as electron holes with positive charge, move through the crystal lattice, producing an electric current. The holes are electron vacancies in the valence band of the semiconductor and are treated as charge carriers because they are mobile, moving from atom site to atom site. In n-type semiconductors, majority carriers are free electrons in the conduction band, moving through the crystal, resulting in an electric current. When a conductor or semiconductor is put within a magnetic field, a Lorentz force appears on charge carriers, which generates the Hall voltage. When a stationary state is reached, the sum of forces should be zero, and assuming the magnetic field is only present in z-axis, we get. And for a negative charge carrier, we get the expression for electric field in epsilon direction, where W is the plate width. We get this expression for Hall voltage. To eliminate the unknown velocity, we use its relation to current, where dq is amount of charge in a small segment, where n is charge concentration and q is elementary charge, while velocity of a charge carrier is getting and expressing velocity. Introducing this into the expression for Hall voltage, we get Hall voltage as well as Hall element sensitivity is therefore dependent on current, magnetic field, sensor element thickness and charge concentration within the plate. A very strong argument for wide usage of Hall sensors in integrated magnetic sensor chips is the fact that they can be produced in a standard CMOS process without any modification. CMOS, meaning complementary metal oxide semiconductor, is the most used technology for integrated circuit production. A plain N-well resistor with a special shape can be used as a Hall sensor. This most certainly is not the case for XMR magnetic sensors. Hall sensors enable building true single-chip magnetic sensors, which by inclusion of additional processing or interpolating electronics evolved into true single-chip encoders such as RLS AM4096. In the next minutes, we will briefly discuss some Hall sensor geometry and material properties aspects that are important for their usage in magnetic sensing. It can be shown that good Hall element sensitivity can be achieved using a symmetrical cross-shaped geometry. Alternatively, square or octagonal sensor shapes are also used, but care must be taken as the ratio of the contact length versus structure perimeter must remain small to achieve optimal sensitivity. The active area of the whole structure is the center of the cross and has constant resistance independent of the cross's size, while its shape remains symmetrical. The cross sides must be kept short to minimize voltage drop over the structure, limiting the useful operational current due to finite chip supply voltage. Sensor size is also an important factor when considering spatial resolution of the sensor. Hall element effectively averages the magnetic field within its active volume. Therefore, with a large sensing element, it is impossible to detect minute variations of the field which would, in an example of a magnetic encoder, introduce unwanted higher harmonics into the sensor output. However, the sensor must also not be too small, that is, too close to the minimum production tolerances of the microelectronics process. This would significantly increase the mismatch between the sensor parameters within a single die and also from chip to chip, meaning that the image of the magnetic field produced by multiple sensors would be distorted again. Besides geometry, Hall sensor sensitivity is strongly dependent on the microelectronics process used for the production, mainly on the mobility and sheet resistance of the N-well layer used. By scaling down the geometry, that is using a smaller process node, the doping amount needs to be increased, meaning that carrier's mobility is decreased. Additionally, smaller nodes require smaller supply voltages, meaning that less current can be pushed through a Hall sensor of a given resistance. All this means that progress of microelectronics to smaller technology nodes brings many challenges to a designer of Hall sensor chips. Let us continue with the processing of Hall sensor output voltage. First, we need to estimate the range of Hall voltage. For a typical supply current of 1 mA and magnetic field amplitude of 10 millitesla and Hall element sensitivity of 100 volts per ampere Tesla, the sensor output would be 1 millivolt. Considering we would like to reach, for example, a 12-bit resolution at a reference level of several volts, the signal would require significant amount in hundreds of low noise preamplification. Another challenge with Hall elements is their offset voltage and their noise. Offset voltage is due to asymmetries in sensor design and production and can reach values similar to the useful signal. Therefore, it is mandatory to eliminate the offset voltage along with the low frequency noise, which presents a significant issue with all CMOS electronics. To resolve the issue, so-called spinning technique is used in Hall sensor integrated circuits. Because sensor offset voltage sign changes after rotating the direction of the current flow for 90 degrees and Hall output voltage does not, we can eliminate the unwanted offset by alternately changing the direction between the input current and output voltage connection. Merging spinning with the chopping technique known from low noise amplifiers can also eliminate the offset voltage and 1/f noise or pink noise of the preamplifier. By chopping and spinning, we effectively move the Hall DC or low frequency signal caused by alternating magnetic field voltage to the part of the spectrum around the selected chopping frequency. By signal demodulation that follows, the useful Hall output voltage is again moved to DC or low frequency, while the offset and 1/f noise is moved around chopping frequency. This introduces a new design requirement for the preamplifier. Its bandwidth needs to be significantly higher, for example 5 to 10 times, than the spinning frequency to prevent losing signal amplitude, while the spinning frequency must be sufficiently above the maximum frequency of the observed magnetic field to ensure its value can be correctly reconstructed. The spinning frequency must also be sufficiently larger than the 1/f corner frequency. That is the frequency where 1/f noise equals the thermal noise. Effectively, this means that due to low Hall signal voltage, the preamplifier gain bandwidth requirement will be almost always at the limit of the chosen CMOS process, and with the low noise requirement, this makes the Hall sensor preamplifier a very space and power demanding design challenge, depending how many Hall sensors needs to be embedded within a single chip. For magnetic encoders, linear or circular Hall arrays are usually employed that can use tens of sensor elements. The Hall element power consumption is therefore significant, and various techniques need to be used to reduce it, such as reducing their duty cycle depending on the sensing requirements. For example, for single pole pair per rotation encoders, such as on-axis, the input frequencies are slow in the range of kHz, so this poses no difficulties. On the other hand, multipole rings can generate high input frequencies close to 100 kHz, making the design more challenging. After signal demodulation, the original whole signal is then reconstructed either by analog filtering or direct AD conversion. Afterwards, further signal conditioning and/or interpolation applies. We hope that this short talk provided some useful insight into the design properties of Hall elements as magnetic field sensors used in position encoders. Stay tuned for other technical topics from RLS.